In this section, we are going to look at how to design counters using flip-flops. So, a counter is a sequential circuit which counts up to a certain value. There are different types of counters. You have n-bit counters, which can again be classified into up counters and down counters. You have something called a mod n counter. There are BCD counters and so on. We are going to start by looking at a simple example, which is a 3-bit binary up counter. So an up counter is a circuit which counts in ascending order, starting from 0, 1, 2, 3 and so on. And because this is a 3-bit counter, it will count from 0 to 7, because 7 is the largest number that can be represented using 3 bits in binary. 7 is represented as 111 in binary. So if you move to 8, it is 1000, which is 4 bits. So a 3-bit binary up counter basically counts from 0, 1, 2, 3, 4, 5, 6, 7, comes back to 0, 1, 2, 3 and so on. So this is the circuit we are going to design today, and for this purpose we will be using JK flip-flops. So irrespective of what counter we are designing or whatever sequential circuit we are designing, the steps are as follows. Step 1, draw the state diagram. Step 2, derive the state table. Step 3, draw the K-maps and derive the expressions for the flip-flops. Step 4, draw the circuit diagram. So we are going to look at each of these steps one by one. So let's start with step 1, draw the state diagram. What is the state diagram? State diagram tells you the sequence of states which the counter follows. For example, to go with our question, which is a 3-bit binary up counter using JK flip-flops, the state diagram would be something like this: 000, 001, 010, 011, 100, 101, 110, 111, and then again 000. So state diagram basically gives you the sequence of outputs which your counter is going to give you in what order. So you connect the different outputs by arrows to indicate the order. So whenever you are asked to design any sequential circuit, be it a counter or shift register or any sequential circuit, the first step is to draw the state diagram so that you know the transition from states. From this state, it moves to this state and so on. So that is our step 1. Step 2 is to derive the state table. So the state table consists of the present state, next state and the flip-flop inputs. So basically when someone tells us to construct a counter or a circuit using JK flip-flops, what they're asking us to do is they're giving us flip-flops and we have to give certain input values for J and K such that the output moves in this order from 000 up to 111 and repeat. Right, so our task is to find out what are the inputs I have to give for the J and K values of each flip-flop. So if we know that, it is just a matter of connecting the appropriate inputs to the J and K locations, and then the circuit runs as expected. I mean, this is for a JK flip-flop example, but irrespective of what you're using, even if you're using an SR latch or a T flip-flop or a D flip-flop, the idea remains the same. If it's a 3-bit counter, you have 3 flip-flops. If it's a 5-bit counter, you have 5 flip-flops. Your task is to identify what are the input connections I have to give to each of the J, K, S, R, D or T values in each of the flip-flops. That is what we are trying to find out, and that is what designing the counter essentially means. So to find that out, we use steps number 2 and 3. First is to derive the state table. So the state table consists of the present state of the outputs, the next state and the flip-flop inputs. And we will use the excitation table for the JK flip-flop to derive the state table. So I will explain in detail what the state table is. So if things don't make complete sense right now, there's no need to worry. But we will first look at the excitation table. So every flip-flop or latch has an excitation table that is has a corresponding excitation table. An excitation table tells you to move from a particular output to a particular output, what are the input values I need to use. So your JK flip-flop has an excitation table which is this. Your SR latch has its own excitation table, your D flip-flop has its own table, your T flip-flop has its own table, but because we are using JK flip-flops here, we will consider the excitation table for JK flip-flop. So J and K are the inputs of a JK flip-flop and Q is the output. Q of T refers to the output at time T. Q of T plus 1 refers to the output at time T plus 1. That is the current and next outputs respectively. So if my current state is 0 and I want to move to 0, my J input should be a 0 and K can be anything, I don't care. If my current state is a 0 and I want to move to a 1, my J should be a 1, K again can be anything. If my current state is a 1 and I want to move to a 0, I don't care what J is, but K has to be 1. If current state is 1 and I want the next state also to be 1, again I don't care what J is, my K has to be a 0. So this is the excitation table for the JK flip-flop. This is something we will be using to derive the state table. Similarly, for whatever flip-flop you are using, you will need the excitation table to derive the state table. So we will now see what the state table is and how to derive it completely. So the state table consists of the following columns: current state, next state, and flip-flop inputs for each of the flip-flops. Now we are designing a 3-bit counter, so we have 3 flip-flops. This is something you need to remember. Whenever you are designing an n-bit counter, you will have n flip-flops, 1 flip-flop to represent each bit, where n is the number of bits, whether n is 3, 5, 10, 100, whatever. So if I am designing a 10-bit counter, I will have 10 flip-flops. So my state table will consist of the current state for all n flip-flops, next state, and the inputs J and K for all the n flip-flops. So for example, if I ask you to design a 5-bit counter using D flip-flop, your state table will have the 5 current states, 5 next states, and D0, D1, D2, D3, D4, because a D flip-flop has only one input D. Whereas this is a JK flip-flop, so you have J0, J1, J2, similarly K0, K1, K2. Now the current state and next state are obvious. Current state, if it is 0, 0, 0, my next state will be 0, 0, 1. If my current state is 0, 0, 1, my next state will be 0, 1, 0. And so on until if my current state is 1, 1, 1, my next state will be 0, 0, 0. How do we get this? From our state diagram. So this much is easy to fill. Now what we do next is we need to fill in these values using this data and using the excitation table. This is the same excitation table which was there in the previous page. I've just written it down here so that we don't need to keep flipping the page every time. So what do we do? Consider Q2 of current time and Q2 of the next time. Check the excitation table and fill J2 and K2 values. Similarly, Q1 current, Q1 next, J1, K1, Q2 current, Q0 current, Q0 next, J0, K0. So we will see what that means. So we will start with Q2. Now my Q2 is currently at 0 and I want it to remain at 0. So everything marked as 2 refers to flip-flop number 2. So Q2 current, Q2 next, J2, K2, they all are one flip-flop. Q1 current, Q1 next, J1, K1 are one flip-flop, and so on. So we will always look at everything pertaining to one flip-flop at once. So we will not mix a Q2 with a Q1 or a Q0. So my Q2 is currently at 0 and I want it to remain at 0. Check the excitation table. Currently at 0, I want it to remain at 0. My J should be a 0 and I don't care what K is. So we will fill that over here. And this is for the second flip-flop. So we will fill that in J2, K2. Similarly, let's say Q2 is at 0 and again I want it to be at 0. Same, 0, don't care. Q2 is at 0, I want it to be at 0. 0, don't care. Q2 is at 0, I want it to be at 1. So we check the excitation table. Q2 is at 0, I want it to shift to 1. Then it is 1 and don't care. So we go back here, we fill 1 don't care. Similarly, my Q2 is 1. I want it to remain at 1. 1 comma 1 is don't care 0. So we go back, we fill don't care and 0. Similarly, it is 1. I want it to remain at 1. Don't care 0. It is 1. I want it to remain at 1. Don't care 0. It is 1. I want it to change to 0. 1 0 is don't care 1. So don't care and 1. So we know what input should be given at every state for the J and K of the second flip-flop. So we do the same process with Q1 current, Q1 next, and Q0 current, Q0 next. We compare the current and next state. We go to the excitation table. We find out what values should come, and we fill them here. When we have done that, this is what our state table looks like. So for every combination of current state and next state, we know what are the inputs our J and K points should receive for each of the flip-flops we are using. So let's take a step back and look at what we were doing. We wanted to design a 3-bit binary up counter using JK flip-flop. So we will have 3 JK flip-flops. For each of those, we need to find out the J and K inputs. That is our objective. So the first step was to draw the state diagram, which is the sequence of states we follow. We did that. Second step was to derive the state table. So state table consists of current and next states and flip-flop inputs for each flip-flop. So current and next states we understood from the state table. For the flip-flop inputs, we selected one flip-flop, let's say flip-flop number 2. We check the current and next states. Let's say it is at 0 and I want it to remain at 0. We go to the excitation table. We see from 0 to 0 what are the corresponding J and K values. We come back, we fill that here. We repeated the same process until the entire table got filled. So this is our state table now. Moving on, our step 3 asks us to draw K maps and derive expressions for the flip-flops. So ultimately that's what we need, right? We need an equation or an expression for the J2, K2, J1, K1, J0, K0 in terms of these Qs and zeros and ones. So we will try to do that. Let us start with J0 and K0 because they are the simplest. We try to draw a K map. The procedure for a K map is as we have studied in our combinational circuits chapter. So we'll start with J0, K0. So we draw the map first. We put Q2 on the left and Q1, Q0 over here. We mark the values. Now we'll start with K0. We look at the values and we see that it takes 0, 0, 0 is an X. So here I put an X. Sorry, I'll make that right. 0, 0, 1 is a 1. So 1. And similarly, you look at the state table. You fill the values. This is what we get. Now the next step in a K map is to group together the ones and don't cares in as large a group as possible. Here, since everything is together, you group them in one thing and you get the expression K0 equals 1. Similarly, if you look at the values for J0 and fill in, here's what you will get. What am I doing here? I am looking at the values for J0 which I got from my state table. I am filling the ones and don't cares in the corresponding locations in the K map. And again, because everything is available, J0 equals 1. Now we'll look at a slightly more involved example. Let's go for J2. So J2, for the first 3 values 0, 0, 0, 0, 0, 1 and 0, 1, 0, it's a 0. So this is a 0, this is a 0, this is a 0. We'll leave these. Coming back, 0, 1, 1 is a 1. 0, 1, 1 is a 1. And all others are don't cares. So we mark these as don't cares. Now we try to group. We can make this one group because ultimately this is what we need. So your expression for J2 is going to be Q1 and Q0 are both 1. So it is Q1, Q0. Similarly, we do the same thing for K2, J1 and K1. So when we have repeated the process for all the inputs, these are the expressions we get. J2 and K2 are both equal to Q1, Q0. J1 and K1 are Q0. J0 and K0 are 1. So we are done with step 3. Draw K-maps and derive expressions for the flip-flops. Step 4 and the final step is to draw the circuit diagram. So we have this basic skeleton, and from this we will try to develop the circuit diagram. We have 3 flip-flops. Each has a J, K and a Q, and each has a clock, a common clock connected to everything. The outputs are Q2, Q1 and Q0, and we have a 1 and 0 line over here. Now we will start from the previous page. We found J0 and K0 are both equal to 1. So we will start by connecting that. So you can see this line here is 1, that goes to J0 and it also goes to K0. Next we found from here that J1, K1 are both equal to Q0. So we have Q0 over here. We take this and connect it to J1 as well as K1. Of course, you make sure that whenever you have an overlap, you draw this kind of a connector and to indicate that there is no intersection. This is just a rough diagram to tell you how we draw the circuit. So I am not paying too much attention on making the diagram neat and clean, but you get the point. Finally, we have J2 and K2 are Q1 and Q0. So you take Q1, you take Q0, connect them by an AND gate, you take that, and that becomes your J2 and K2. So this is what your 3-bit counter looks like. So to quickly summarize, we drew the state diagram. We constructed the state table which has current state, next state and flip-flop inputs. We derived the flip-flop inputs using the excitation table. Then we drew Karnaugh maps and identified the expression for each input J1, K1, J0, K0, J2, K2. Then we connected the appropriate gates and terminals using a circuit diagram. So this is a 3-bit binary up counter. So when you connect 3 flip-flops in this fashion, it will count from 0, 0, 0 to 1, 1, 1 and again 0, 0, 0 and so on. So as an exercise, I would like to give you a couple of examples. A 3-bit binary down counter, which is something that counts from 76543210, 76543210 and so on, using D flip-flops. And a 3-bit up-down counter. Up-down counter is something which counts from 0 to 7 and then 7 to 0, again 0 to 7, 7 to 0 and so on. So this is what the state diagram for that would look like. So these are examples which will help you understand better.